In today's video, I'll be talking about sound intensity. First, we have to understand what power is. The amount of energy transferred per second is called power, and that's the power of the wave, and that would be how many joules per second. Sound intensity, is defined as the power that passes perpendicularly through a surface divided by the area of that surface. So intensity is equal to power per unit area. And if you look at the two people listening to a speaker, obviously person 1 will hear a larger intensity than person 2. And the reason being is that at person 1, that same amount of power is going through a smaller surface area than with person 2. So let's try an example. We have 12 times 10 to the negative 5th watts of sound power passes through the surface labeled 1 and 2. And you're given the area of each of those two surfaces. And you want to know what the sound intensity is for each of the two surfaces. So it's the same amount of power, but it's being spread across more area in the second case. So the intensity goes down. So you can see in the second case, since there's more area, 12 meters squared, the power per unit area will be less. Alright, if we assume the sound travels in all directions from the source equally, or it goes out like in a sphere, then we get this equation, where it's still power per unit area, but the bottom is the surface area of a sphere. So if you look at this closely, you have the intensity is equal to 1 over the distance between the source and the observer squared. So it's an inverse relationship. So you might be using this equation as well. All right, let's try a conceptual example. You have a person singing in the shower. Their voice, for simplicity, is shown in 3 different directions. One here, it's going up, hitting the shower roof and coming back down. One hitting the floor and going back down and back up. And one a direct route. And the question is, at distance r in front of the person, does the equation for the intensity of sound emitted uniformly in all directions underestimate, overestimate, or give a correct sound intensity? Alright, so the equation we just learned, is that going to give us the correct value for the intensity at this point? Okay, using this equation. And the answer is no. The equation really is only valid for direct sound routes and does not account for the added energy of the reflected waves. So it didn't add this, nor did it add this to it. Okay? All right, here's another way of looking at sound intensities. If you have a speaker creating a sound wave, it sends a series of high pressure and low pressure regions. The higher this pressure is, the higher the amplitude is, like I'm showing a transverse wave here to mimic what's actually happening here. Now obviously it's not a transverse wave, but this is easier to see. The higher this pressure is compared to this pressure, the more intense the sound is, the more power it has. And we notice that as being loudness. Loudness depends primarily on the pressure amplitude of the waves. And this correlates to energy, the more energy the wave has. All right. Our hearing does not treat all frequencies equally. Now, what this is a drawing of intensity on the y-axis versus frequency on the x. And obviously this scale is not linear. It's all over the place if you look at it. And that's just so it fit into a nice, easy, manageable space. You can notice here a few things as we go through this. We don't hear all frequencies the same. Some frequencies, like down here, we hear at a much lower intensity than way up here. Another thing to notice, it's not on here, but just a fact, is as we age, our hearing range narrows. This graph here is showing between 20 and about 20,000 hertz is what we normally hear. But if you notice here, very low intensity, low frequency or very high frequency waves have to be incredibly intense for us to detect them. All right, the lowest point that we can hear at is called the threshold of hearing, and that varies per frequency. As I stated before, some frequencies are easier to hear than others. And this area up here, which is called the threshold of pain, is which, when you hear that sound, it actually physically hurts. That actually stays somewhat steady. And to emphasize the fact that they both vary with frequency. So how sensitive are our ears? This is kind of interesting that we can detect a pressure change in the air around us of 1/10 of a billionth of an atmosphere. So the variations between those high pressure regions and low pressure regions are incredibly small, and our ears are sensitive enough to pick that up. Some of the things to notice about this is our speech range is anywhere between 100 hertz, the lowest sound we can make, up to around 8,000 hertz. But musical instruments have a much larger range, and what we can hear is even larger. So, if you look at this, what frequency do you think we hear the best? Take a moment, look at the chart, and see what frequency we hear the best. Hopefully you're able to detect that it's around 3,300 hertz, which is right around here someplace, and that's a guesstimation. So as long as you knew it was around here someplace, you did well. Human hearing depends on both frequency and the intensity of sound. For sound to sound twice as loud to us, we must increase the intensity of the sound about 10 times. So in other words, our hearing is approximately logarithmic. For a sound to sound twice as loud, it really has to have about 10 times the intensity, or power per unit area. For it to sound 4 times as loud, it has to have 100 times the intensity. And 8 times as loud, 2 times 2 times 2, it would have to have 1,000 times the intensity. Now here's a table that measures intensity to a relative scale called decibel level, where at a intensity of 0 decibels correlates to an intensity of 1.0 times 10 to the negative 12, and that's known as the threshold of hearing. And every time this goes up by a factor of 10, the decibel level goes up by a factor of 10. So the decibel level is only a measure of relative intensity. And it's based on, as I said, this threshold of hearing, called 0 decibels. And what I'd like to do is determine how much louder and how much more intense it is going from like a whisper to a vacuum cleaner. So a whisper is at 30 decibels, or 1 times 10 to the negative 9th watts per meter squared, to a vacuum cleaner, which is 70 decibels. Now obviously all these decibel ranges depend on how far away you are from the source of sound, because as we know it's an inverse squared relationship. So the closer you are to one of these things, the louder it will be. So if we go from 30 to 70 decibels, every time we skip, go up 10 decibels, it sounds twice as loud. So from here to here is 2 times as loud, from here to here is 2 times as loud, from here to here is 2 times as loud, from here to here is 2 times as loud. So it sounds like it's 2 times 2 times 2 times 2, or 16 times as loud. And as we go up 10 decibels, the intensity increases tenfold. So it's about 10,000 times as intense. Okay? And here's a relative chart that you might find interesting about different decibel levels, and some ideas, like a jet fly over 1,000 feet, how many decibels that would be. This is pretty good I like this one a lot better because it actually tells you how close you are to it. For a gas lawnmower, 100 feet away, it's around 70 decibels. But obviously, if you get a lot closer to it, it's going to be a lot louder. Excuse me. Some other things to note is on the AP exam, there really won't be any problems with decibel levels, but you should understand the relative idea of it and how decibel levels relates to intensity. Okay, and that's it.